This is Maths 12, and we've got some rates from graphs. So just what's going on in this experiment? Well, we've got oxygen produced from hydrogen peroxide and catalase. So just in any enzyme experiment, it's wise to just decide what's what. Now we've got, that's our enzyme. Hydrogen peroxide, that's our substrate, and the volume of oxygen is our product. Product, substrate and enzyme. And we can see this is our volume of product there. And we've got time on the bottom. So over the course of this experiment, we produce our product pretty fast at first, and then we eventually level off and there's no more product made no matter how long we leave it. We've got two lines on here. We've got our X and Y. So X, what's that? That's the initial. So that's our initial rate of reaction. And then Y is going to be our, what is Y? That's our actual investigation. So that's our Y investigation. So two different lines on this graph. Calculate the initial rate of reaction. So this is our initial rate of reaction, and as it's a straight line, that rate of reaction is constant. So we need just to decide what a rate is. So a rate is something something, I'm going to write something per unit time. So how much happens per unit time? So for example, miles per hour is a rate of a car. In this experiment, the rate is a rate of product per second. So in here, this is volume of oxygen per time is second, or cm cubed per second, or cm cubed per second, like that. So that's our rate. And so we've got part A, the initial rate. So that's our purple there. So this is our initial rate, and we could measure this anywhere on here, but it's possibly easiest to actually, where the end of this is, we're going to make a triangle. So that's going to go down there, and we're going to put it across where there it is on there. So we move this to there, and that is 9.4, and this is 30. So our triangle is kind of this. So in 30 seconds it's gone up 9.4 cm cubed. So it's gone 9.4 per 30 second. So 9.4 cm cubed in 30 seconds. You could work that out per second. So you could go in your calculator, 9.4 divided by 30 is that. So 9.4 divided by 30 equals 0.31, and the units cubic centimeters per second. We could, that's fine, we could times that by 60 to get it into minutes, possibly. So if you've done it in minutes, times it by 60 is 18.8. And we've times it by 60 there. Or you might have just gone, well, if that much is in 30 seconds, I know how much is in minutes, that's times it by 2. 9.4 times by 2 is 18.8. Okay. Now we're on to our, so if that was our initial rate there, we now put that pen away and get this pen out, and this is our kind of investigation. So we need to use this other line. So for the first 20 seconds of our investigation, so there's 20 seconds there. So we are, helpfully there's a little cross there as well. And this one has gone across 20 and it's gone up 4.3 on there. So B1 is, it's gone up by 4.3 centimeters cubed in how many seconds? 20 seconds. So 4.3 divided by 20 is 0.215 centimeters cubed per second, or 0.22 if you were rounding off to a sensible number. So I'd go equal 0.22 centimeters cubed per second. You could times that by 60 to get it into minutes if you were doing that in minutes. So that's 12.9 centimeters cubed per minute. And if we were looking at part 2, between 60 and 80 seconds, so 60 and 80. So I'm going to so 60 and 80. And I want to see how much it's gone up. So that's 20 seconds, is that? How much has it gone up? Slightly more difficult to read this, but it's gone up from 8 to wherever that one is. We'll read that off in a second. So in that 20 seconds it's gone up by how much? It's gone from 8 to halfway between 8 and 9, so it's gone up 0.5. So the difference is 0.5 cm cubed in 20 seconds. Can't even write 20 seconds. 20 seconds. So 0.5 divided by 20. 0.5 divided by 20 is 0.025 centimeters cubed per second. And again, if you're doing that in minutes, times that by 60 is 1.5. 1.5 centimeters cubed per minute. And of course it is. If not half in 20, well, if you do times that by 3, that makes sense for that. And then explain the difference between the initial rate and the investigation rate. It's a bit of it's not very well constructed, this question, but it's really saying is what's the difference between my pink line, initial line. Why is my rate of investigation sort of start off the same and then get slower? And the difference there is, in the investigation we're actually using up some of our substrate, so there's less chance of a collision between the substrate and an active site. So in the investigation, the substrate is being converted to product. So less substrate to collide with enzyme active sites. So rate is less. So that explains why this investigation line is underneath the initial. So the initial is the kind of perfect rate of lots of substrate, maximum amount of substrate available. D is explaining why the rates at 0 to 20 is different to 60 to 80. So I'm going to use a different colour here. So 0 to 20, this area here, kind of yellow. So 0 to 20 seconds, and then we've got I'm not quite sure about a choice of colours here. Let's have green. Let's have a light green, and then 60 to 80 is this. That sort of. So the rate at the start, more substrate. So essentially it's this more substrate, more chance of a collision. So more substrate, more chance of a collision. And then 60 to 80, well, there's lots of product hanging around but not much substrate now. So the chance of a substrate colliding with an enzyme active site is reduced. So less substrate available, so less chance of a collision between substrate and enzyme active site, or less chance of an enzyme enzyme substrate complex forming. It's all this just the idea about collisions, and if you've got lots of things there, there's more chance of a collision. If there's less things there, there's less chance of a collision.